Have you ever pictured an eruption without fire? Start with Io, Jupiter's restless moon, where lava lakes burst through sulfur plains and volcanoes rise taller than Everest's neighbors. Shift to Enceladus, a small world that trades magma for water. Jets of ice and salt shoot from its south pole, hinting at a hidden ocean below. Then Triton, circling Neptune backward, sends dark plumes skyward from nitrogen-rich ice. Different engines, same idea. Energy pushes material up and out, rewriting a surface in real time. Back on Earth, the Hunga Tonga Hunga Ha'apai blast punched through the stratosphere and rang the planet like a bell. If clear, grounded exploration is your pace, a like and subscribe helps others find it. Settle in. This is the story of the biggest eruptions across worlds, across elements, across time. We begin where eruptions are hottest, Io, the innermost of Jupiter's major moons. Among the many worlds circling the giant planet, this one shows behavior we rarely see in a place so small. Persistent volcanoes, dancing auroras, and a thin, sulfur-rich atmosphere that is remade again and again. Think of a rocky body close in, under constant stress, warmed from within, not by sunlight, but by gravity itself. That is Io's setting, and almost every feature that makes it unusual follows from that setting. Jupiter hosts a crowded system. Astronomers have confirmed dozens of moons there, 79 and counting, as new small ones are found. A handful skim near the planet, moving in the zone where rings and dust also orbit. Far more important for our story are the 4 large bodies discovered in 1610 with one of the first telescopes. We call them the Galilean moons. Keeping their order helps make sense of their roles. From the inside outward, Io, Europa, Ganymede, and Callisto. Beyond those heavyweights, many irregular moons follow distant, tilted, or backward paths, but they do not drive the main tides that shape Io. The crucial players sit close, the planet itself and its next 2 big neighbors. Io's track hugs Jupiter. The moon circles only about 350,000 kilometers above the cloud tops, a gap small enough that the planet would dominate its sky. If you stood on Io and looked up, Jupiter would span an area about 39 times that of our full moon, as seen from Earth. That scale matters because apparent size reflects how intense the gravitational gradient feels across a body. The nearer a moon is, the harder one side is pulled compared to the other. Io does not drift slowly around over weeks. It completes a lap in roughly 42.5 hours. So every 2 Earth days, its surface faces the full cycle of push and pull again. The motion is not isolated. Io's path is locked in step with those of Europa and Ganymede, a pattern called orbital resonance. Here is the simple rule. For every orbit Ganymede makes, Io goes around 4 times. For every Europa orbit, Io makes 2. A resonance is more than a neat ratio. It keeps the timing of gravitational tugs regular and strong. Each time these moons line up, their pulls arrive on schedule, like a child pumping a swing with the right rhythm. Because the tugs repeat at the same points in the orbit, Io's path does not settle into a perfect circle. It stays a little stretched. Astronomers call that extra stretch eccentricity. That tiny deviation is enough to feed energy into the moon's interior every cycle. The outcome is tidal heating. When a world follows an eccentric path around a massive body, it is squeezed and released again and again. Rock is not perfectly rigid. Under stress, it flexes. and when it flexes, it warms, the way bending metal slowly heats in your hand. Inside Io, this constant kneading turns orbital energy into internal heat. The effect is so strong that geologists expect the shape of the moon to bulge and relax through each lap. At moments in the orbit, the tide on the solid ground is estimated to reach on the order of 100 meters from low to high, a huge number for rock. That rise is not a wave of water but a slow lift of the crust itself. A comparison helps. On Earth, the moon and the sun raise tides in the oceans and, to a lesser degree, the crust. Typical sea level changes at calm coasts run a couple of meters from low to high, and the vertical flex of solid ground is usually measured in centimeters. Our planet sits at a comfortable distance from its main tide-raising body, so the differential pull is modest. Io has no such comfort. Because it orbits so close to the largest planet in the solar system, and because the resonance preserves its slight eccentricity, the differential forces are several times stronger than the Earth-Moon case, enough to keep the interior working. The important point is not the exact multiplier, but the permanence of the input. The moons around Jupiter do not let Io relax back into a perfect circle, so the stress never fully turns off. One more piece fixes the view from the surface. Io keeps the same face toward Jupiter at all times, a state called tidal locking. A day on Io equals its orbital period, so one hemisphere always sees the planet and the other always faces away. This is the same behavior we know from our own moon, which shows a single near side to Earth. Tidal locking is common around giant planets because the gravitational torque drains rotational differences over time. For Io, it means long-term stability in the direction of stress and a stable pattern of heating zones that shift mostly with the orbit rather than with daily spin. Size and weight also shape what follows. Io is the second smallest of the Galilean moons, but it is not small in an absolute sense. Its diameter sits close to that of Earth's moon, which helps listeners anchor the scale. The densities are similar as well, so the surface gravity on Io feels familiar in rough terms. Low compared to Earth, but not as weak as on tiny asteroids or porous comets. Here, the key distinction is not how big Io is, but what it is made of and how packed that material is. Among all the moons in the solar system, Io ranks at the top for density. Dense bodies tend to be rich in heavy rock and metal, and poor in light ices and gases. Composition confirms that idea. Io is built mainly of silicate rock minerals like those in Earth's crust and mantle, and iron. That mix places it closer to the inner, rocky planets than to most large moons, which commonly carry a great deal of water ice mixed with silicates. Where Europa, Ganymede, and many outer moons store thick layers of ice or even global oceans under ice shells, Io is dry. In fact, it likely has the least water of any known body in the solar system. Without much water to buffer temperature or trap heat, and with constant kneading from tides, the rock itself becomes the fluid carrier of energy. When it softens or melts, it moves as magma rather than as liquid water. Inside, the structure follows a simple layered picture. At the center sits a core of iron or iron mixed with sulfur to form iron sulfide. Above that lies a thick mantle of silicate rock, and on top a crust made of cooled silicates, coated in sulfur and sulfur dioxide, compounds from eruptions. The presence of metal at the center is not surprising given the density. What matters for the magnetic behavior is whether that core is convecting, moving, and stirring in a way that could generate a magnetic field. Observations show no global magnetosphere surrounding Io, That absence suggests the core is not currently driving a dynamo, or at least not one strong enough to stand out against Jupiter's powerful field. Instead, Io sits inside the giant planet's magnetosphere and interacts with it, which helps explain some of its auroral glow. The mantle is where the thermal story turns into surface change. Under the crust, heat from tidal flexing accumulates. Rock near the top of the mantle reaches temperatures where it can partially melt, forming pockets and channels of magma. Models and observations point to a layer beneath the crust that behaves like a magma-rich system tens of kilometers thick. In many places, this layer may be largely molten or at least a connected network of melt that allows material to move. Estimates place its thickness at no less than about 50 kilometers. From that zone, eruptions reach the surface through fractures and vents. What we see as towering plumes and bright lava flows begins there, in the warm, deforming mantle just below the rigid outer shell. This is the source region for Io's volcanism, the place where internal stress is turned into molten rock and pressure, and from which the visible activity rises. From those mantle-fed fractures, the scale becomes clear at the surface. Hundreds of active volcanoes scattered across nearly every region. This is not a surface dotted with a few vents that wake once in a while. It is a world where heat finds many paths upward, where plumes rise into space and fresh deposits paint the ground in bands and rings. Before the 1,970 seconds, almost none of this was clear. Telescopes on Earth showed a small disk and a hint of unusual color, and careful measurements suggested the surface lacked water and might hold sulfur. But those were clues, not proof. Io's nature came into focus only when the first spacecraft moved close enough to see patterns, measure textures, and catch activity in real time. Pioneer 11 was the first mission to give us any real detail. Its images were rough, by today's standards, grainy, low resolution, hard to interpret, but they did enough to change the category of Io in our heads. The data pointed to a rocky body, not a frozen one. Silicate rock means minerals made of silicon and oxygen, the same basic stuff as Earth's crust and mantle. That finding alone separated Io from many outer moons, which are heavy with ice. Pioneer 11 also detected a thin atmosphere. Thin here means the gas above the surface is so slight that it would count as vacuum by everyday human experience. You would need a pressure suit to stand there. But for scientists, even a trace gas is a big clue. It hints at what is being released from the ground and how sunlight and radiation change it. Pioneer 10 was also said to take close views of Io, but it ran into the harsh reality of Jupiter's environment. The giant planet sits inside powerful radiation belts. These are regions filled with charged particles moving at high speeds, guided by the planet's magnetic field. When Pioneer 10 crossed those belts, the radiation level was about 10,000 times higher than the worst zones around Earth. That kind of exposure can flip bits in computers, jam sensors, and disrupt commands. The spacecraft lost the ability to carry out the close-up imaging plan for Io. From a safety point of view, the result is not surprising. From a science point of view, it was a reminder. To study this system, we need machines that can operate inside conditions far more extreme than those near our planet. The big leap came with Voyager 1 and Voyager 2 inches 1,979. Voyager 1 passed only about 20,000 kilometers from Io. At that distance, features only a few hundred meters across can leave a mark in the images, and patterns across wide areas become vivid. What appeared was a landscape unlike any other seen up to that point. The colors were not muted grays or whites. They were bright yellows, reds, blacks, and whites, blended in swirls and rings. Even more telling was what was missing: impact craters. On the Moon, Mars, and many other bodies, old craters cover the surface like pockmarks that never heal. Io showed almost none. The simple reason is constant renewal. If lava, frost, and plume fallout keep burying old ground, craters do not last. That absence is a strong, direct sign of active geology. Voyager 1 also spotted mountains that rise higher than Mount Everest's summit above sea level on Earth. But these are not volcano cones. They are great blocks of crust pushed up by internal stresses, sometimes with steep, broken sides. The craft saw volcanic pits hundreds of kilometers wide. A pit here is a broad sunken area with sharp rims, often called a caldera, when tied to magma moving out from below. The wide pits hinted at large reservoirs or networks of molten rock under the crust. Across many areas, dark or bright streaks and sheets traced what looked like lava flows, sometimes with a glossy look where they had cooled smooth. Then came the decisive observation: plumes rising from the surface. In the images, arcs and umbrellas of material stood above the limb of the Moon, backlit by space. These were not slow hazes. They were jets shooting hundreds of kilometers high. That sight was proof of present-day volcanism. Up to that point, no one had ever seen an erupting volcano beyond Earth in real time. Later, we would learn about cryovolcanoes, cold eruptions of water and other volatiles on other worlds. But on Io, the activity is driven by heat that melts rock, not ice. Voyager 1 thus became the first mission to witness visible, high-temperature volcanism off Earth. The colors began to make sense as well. Voyager 1 confirmed that much of Io's surface is coated in sulfur in different forms, often called sulfur frosts, when they settle from gas onto cold ground. Sulfur can appear yellow when elemental, white when it binds with oxygen as sulfur dioxide, and red or black when altered by radiation or mixed with different phases. The same compounds dominate the faint atmosphere. When fresh gas vents from a volcano, it expands, cools, and can freeze back onto the surface as frost. Sunlight and charged particles then break and reshape these molecules, shifting their appearance over time. That cycle vent, frost, alter helps explain the bright patchy look. Voyager 2 flew by in July 1979, but it did not come nearly as close. The distance was around 1 million kilometers, so the images could not match the sharpness of Voyager 1's close-ups. Even so, Voyager 2 saw 7 of the 9 plumes that Voyager 1 had recorded 4 months earlier. That simple overlap told a clear story. Some eruptions on Io last a long time by human standards, staying active for months or longer. These are not brief flashes that appear and vanish overnight. Continuous or frequently recurring plumes mean steady supplies of gas and particles, steady venting, and continued burial of older terrain. The next wave of insight arrived with the Galileo spacecraft, which entered orbit around Jupiter in 1995. Galileo was not optimized for Io from the start. It had to study an entire planetary system. Worse, it suffered mechanical problems that limited its data return. The most serious was a high-gain antenna that failed to fully open, cutting the rate at which it could send images back to Earth. Other issues affected instruments and moving parts. Even with these constraints, Galileo captured some of the highest resolution views of Io we have, including small-scale textures in lava fields, crisp edges of pits, and the bases of plumes. Galileo's instruments confirmed key points about what Io's volcanoes release. Some eruptions send out sulfur-rich gases that freeze as bright deposits nearby. Others produce silicate magma's molten rock, similar in basic chemistry to basalt and related volcanic rocks on Earth. Measurements and models also indicate that many of Io's magmas are rich in magnesium, which implies higher temperatures and specific mineral mixes when the melts cool. On Earth, basalts with more magnesium tend to come from hotter mantle sources and can be more fluid when they erupt. On Io, high magnesium magmas fit with the strong internal heating from tidal flexing. Seen at global scale, Io's surface is a patchwork of color driven by composition and age. Wide yellow plains are mostly elemental sulfur, laid down in sheets and dusts. Bright white areas are fresh frosts of sulfur dioxide, often renewed by recent gas release and quick cooling at the surface. Where those white patches appear clean and unbroken, the frost is young. Where they are streaked or darkened, space weathering and warm ground have worked on them. The polar regions look different again. Near the poles, intense radiation from Jupiter's magnetosphere alters sulfur more quickly, breaking bonds and driving color changes. That damage shows up in images as deeper reds and browns compared to the rest of the moon. Red tones appear elsewhere for another reason: fallout from plumes. When a high plume erupts, gas and tiny particles spread out and fall back down in a ring around the vent. Over time, that ring can widen and darken as the composition shifts and as radiation cooks the deposit. The most striking example on Io is tied to the volcano Pele. Pele sits within a large volcanic depression and, during some periods, sends material high into space before it settles. The fallout forms a broad, red ring that stands out even in distant images. When Galileo was operating, Pele was in a quieter phase and did not show its largest plume, but Voyager 1 had caught it at the right time, years earlier. One famous image from Voyager 1 shows a plume at Pele reaching about 300 kilometers in height and spreading to about 1,200 kilometers across. To translate that scale, the umbrella of the plume would cover an area roughly comparable to the size of Alaska. The height is not a solid column. It is a fountain of gas and fine particles, rising, cooling, and falling back under gravity. The sheer size points to strong vent pressure and significant gas content. Eruptions like this do more than draw patterns in the sky. They seed the surrounding plains with new material, change the ground's reflectivity, and feed the thin atmosphere with fresh sulfur compounds. All of these results add up to a picture of a world that is active in multiple modes at once. Some vents release jets that build huge, temporary canopies. Other places leak lava slowly, advancing in sheets that either glow hot or cool to dull colors. Mountains rise where the crust is pushed and broken. Pits open where magma moves out or empty chambers collapse. The pace is fast enough that maps can go out of date over a few years. For scientists, this means that each flyby can show new features or erase ones seen before. For the physics, it means tidal heating is not just a gentle background. It is a driver that constantly remodels the outer shell. Color, composition, and form are only part of the story. Location matters too. Many of the white and yellow plains sit downwind of active centers, shaped by where the plume clouds travel before they fall. Darker flows tend to trace low ground or cracks where the crust has opened. The poles where their radiation damage like caps. Over this canvas, Jupiter's magnetosphere sweeps electric currents through Io's atmosphere and surface lighting up auroras in spots that shift with the moon's path. The interaction is complex, but the visual result is clear. Patches that glow at specific wavelengths and move with predictable timing. A last point in this segment is about shape and source. On Earth, when you look for where lava comes out, you often start at the top of a volcano. Many volcanoes have a summit depression, a crater, or a caldera where gases and magma can escape. Those summit features feed flows down the sides. The rule is not perfect on our planet. Some eruptions break out on flanks or along rift zones, but the common picture is a peak with a vent at or near the top. Io breaks that picture in obvious ways. The towering peaks that rise like tilted blocks do not carry classic summit craters. The high places, split and sharp, do not host the deep bowls that act as sources for lava on Earth. The flows and pits that feed the most dramatic activity tend to sit away from those high peaks, in broad depressions and plains, not at the crests. And unlike the volcanic cones we know so well, those depressions are not found on high peaks on Io, so the sources sit low. Instead of tall cones with open craters at the top, Io often presents broad lava lakes bordered by raised walls. These rims mark the edge of large depressions called calderas, where the ground has sunk over a magma reservoir. The biggest of these on Io is Loki, a volcanic depression about 200 kilometers across. A feature that wide would nearly span some small countries on Earth. Loki is not just large, it is connected directly to melt below. Most of the time, its surface carries a thin, solidified crust, a cooled skin that floats on top of a much hotter, liquid interior. This skin looks dark and steady from far away, yet it is temporary. Heat builds from below, gases escape through cracks, and the crust thickens and cools until its own weight and weakness cause patches to founder. When sections break and sink, fresh magma rushes up to fill the gap, and the lake brightens sharply in infrared and visible light. On average, Loki alone puts out about a quarter of Io's total heat flow. That fraction is striking, given there are hundreds of other active centers. But Loki does not stay at average for long. During overturn events, when large plates of the crust sink back into the molten interior, the power can rise by roughly an order of magnitude. Instruments then detect Loki producing 10 times more heat than its usual state. The change is not random. It follows the physics of a crust that grows, insulates, and finally fails, after which the cycle resets with a new, thinner skin. The pattern is similar in other large calderas. Across Io, a lid forms, cools, buckles, and is swallowed, exposing incandescent melt and releasing gas into the thin atmosphere. A clear view of this behavior comes from another major volcanic site called Tvashtar. In typical images, Tvashtar shows the quiet face of a lava lake, dark tones, some warm edges, a smooth surface broken by a few cracks. During active overturn, the scene transforms. Bright curtains of lava rise along fissures, fresh crust breaks and slides under, and a shower of hot droplets and gas fills the air above the lake. In near-infrared frames, where heat is most obvious, the emission can be so intense that electronic detectors saturate. The camera records those pixels as pure white, not because the surface turned white, but because the signal exceeded the sensor's range. It is a simple way to see how energetic the process is. When rock glows hot enough to overwhelm the instrument, a great deal of power is leaving the interior. In 2007, a different spacecraft added a dramatic chapter to this record. New Horizons flew past Jupiter for a gravity assist on its way to Pluto. That brief pass let the mission test cameras and spectrometers in a challenging environment and capture snapshots of the Jovian system. The team pointed the instruments at Io, and Tvashta was in full eruption. The plume reached hundreds of kilometers above the surface, forming an umbrella shape that stood against the black of space. In some frames, you can trace the shadow of the plume across the ground like a long, soft-edged mark. Around the disk of Io, several smaller eruptions appeared at the same time, short jets, glowing cracks, and hot spots along fissures, evidence that the moon's activity is distributed and often simultaneous. The combination of a towering plume and many less events shows how the tidal engine powers events at multiple scales. Although many of Io's volcanoes present as low calderas and flat-floored lakes, the moon also hosts very tall mountains. The highest rise to about 18 kilometers above their base, more than twice the height of Everest above sea level, yet they are not part of long ranges. They stand alone, with steep faces and complex, broken flanks. Most of these mountains are not volcanic piles built by lava stacking up. Instead, they are uplifted blocks of crust, tilted and thrust upward by deep stresses. Lava lakes often lie nearby, which hints at the local structure. Faults in the crust provide paths, both for large-scale block movement and for magma ascent. Where the crust is pulled apart or pushed together, molten rock finds room to collect, and pressure finds a way to escape. The pairing of lonely mountains and adjacent calderas marks regions where the outer shell is especially active. Io's uniqueness does not stop at the ground. Its environment is shaped by Jupiter's enormous magnetic field, which fills the space around the planet and traps fast-moving charged particles. Io orbits within some of the strongest parts of this magnetosphere. When gas escapes from Io's volcanoes, sulfur, oxygen, sodium, and other species, it can form a very tenuous envelope around the moon. Some of these neutral atoms and molecules drift away and spread along Io's path, creating what scientists call a neutral cloud. Neutral means the atoms carry no net charge. The cloud is not thick like a terrestrial fog. It is a very thin, extended population of particles that slowly circulates near Io's orbit and beyond. Farther out from Io's immediate surroundings, there is another key structure, the Io-plasma torus. A torus is the shape of a donut, and in this case, the donut is made of ionized gas atoms that have lost or gained electrons and now carry charge. The torus is centered on Jupiter's magnetic equator and tends to corrotate with the planet's magnetic field. Corrotation means it sweeps around nearly as fast as Jupiter spins, which is much faster than Io moves in its orbit. Typical speeds in the torus are on the order of 70 kilometers per second, while Io orbits at about 17 kilometers per second. Because Io passes through the middle of this torus, the charged particles in the torus stream past the neutral cloud and the thin atmosphere around the moon like a stiff wind. Collisions and interactions in that wind have clear effects. When fast ions from the torus strike neutral atoms from Io, they can knock off electrons and turn those neutrals into new ions. Once ionized, the particles respond to magnetic fields. Many are drawn into the torus and begin to corrotate with Jupiter. In this way, Io feeds the torus continuously. Measurements suggest that neutral material is converted and lost from Io's cloud into the torus at roughly a ton per second. Over time, this steady supply increases the mass and pressure of plasma in Jupiter's magnetosphere, helping to inflate it. If human eyes could see the magnetosphere from Earth, and if it glowed as big as its extent, its apparent size on our sky would rival that of the full moon. It does not shine that way, but instruments that sense charged particles and radio waves register its giant reach. The coupling between Io and Jupiter is not only about particles drifting and colliding. The magnetic field lines that thread past Io act like wires in a generator. As the torus plasma sweeps by and Io moves through the field, an electric potential builds between different parts of the moon and the surrounding plasma. This drives a current along a bundle of magnetic field lines linking Io to Jupiter's polar atmosphere. That current system is called the Io flux tube. A flux tube is simply a set of field lines carrying concentrated current and plasma. On the Sun, related structures connect sunspots and guide glowing material in loops. At Jupiter, the Io flux tube carries energy and particles downward into the planet's upper atmosphere near the poles. Where the current enters Jupiter's atmosphere, it excites gases and creates an auroral spot, often called Io's footprint. That footprint moves with Io's orbital position and can show a bright core and a trailing arc, like a comet-like streak in the auroral oval. Energy flows both ways along the tube, and waves launched in the system can travel around the magnetosphere, adding structure to the torus and to Jupiter's broader auroras. The whole process is a clean example of electromagnetic induction on a planetary scale. Motion through a magnetic field generates voltage, currents flow, and the result is light where the current lands. Auroras also occur on Io itself. Because Io is bathed in Jupiter's magnetic field and sits inside the torus, electrons and ions constantly rain onto its surface and pass through its thin atmosphere. When these charged particles hit atoms and molecules above the ground, they can excite them to higher energy states. As the particles relax back down, they emit light at specific colors tied to the element. On Earth, we are used to auroras near the poles because our magnetic field funnels particles there. On Io, the geometry is different and the atmosphere is thin and patchy, so the glow is not limited to classic polar ovals. Bright spots and swaths appear at various latitudes, often tied to volcanic centers and to the path of the flux tube. The colors help identify the sources. Green is sodium, red is oxygen, and blue from sulfur. By late December, the submarine volcano Hunga Tonga Hunga Ha'apai had entered an active phase. Activity came in pulses, venting, ash bursts, and brief explosions, each one adding fresh material to a growing cone and clearing the throat of the system. Local scientists watching the area reported another burst on January 14. From the ground, it looked dramatic. A grey column rocketing upward and spreading, a vertical pillar that seemed to puncture the sky. Instruments measured ash and gas reaching roughly 20 kilometers, a height that lifts material into the lower stratosphere. The image from sea level made the column feel massive, yet from geostationary orbit, where weather satellites hold still above a fixed point on Earth, that tall pillar registered as a small, bright spike on a planet-wide disk. Scale flips with distance. What dominates a local horizon can shrink to a pinprick from space. The next day changed the picture completely. Both GOES West and Himawari 8, two geostationary satellites that monitor the Pacific, captured an eruption so large and fast that it rewrote how a volcanic blast looks in real time. In a matter of minutes, a dense, towering cloud rose and then spread in a circular shield, rippling the surrounding air as if a stone had been thrown into a pond the size of an ocean basin. The expanding edge showed scalloped waves and bright, overshooting tops. Initial assessments compared the total energy to human-made nuclear tests, and early estimates suggested the blast could exceed even the largest of those. The comparison is not meant to dramatize. It is a way to convey the order of magnitude. When you overlay the footprint of the main cloud on a map of Europe, the circle covers a striking area. Country after country falls under its diameter. That footprint is only the plan view. In depth, the cloud pierced high atmospheric layers, and the umbrella reached outward with a sharp, fast-moving rim. Inside the plume, the atmosphere behaved like a laboratory for charged particles. Radio frequency sensors that listen for impulsive electromagnetic signatures counted more than 200,000 lightning flashes during the event. Volcanic lightning is still an active research topic because it is hard to observe safely and comprehensively. The mix of hot gas, fine ash, and water vapor rises quickly, collides, and fragments. Those collisions separate charges, much like in a thunderstorm, but the details differ because the particles are ash-rich and the plume geometry is unique. Current studies suggest that positive and negative charges build in different regions of the cloud. Some charges may come directly from the eruption column via triboelectric effects, charging by friction and breakage of particles, while others arise from rapid freezing and melting of water mixed with ash and from interactions with the bay. Surrounding air. The result is intense, clustered lightning that can be mapped from space and from distant ground stations, even when the plume itself blocks a direct view. The island built by earlier eruptions was uninhabited, but nearby populated islands sat within reach of many hazards. Damage from a volcano is not a single thing. It comes in layers that unfold with time. The first layer is ashfall. As the umbrella expanded and winds took hold of the cloud, fine particles settled over Tonga. Photos and satellite images show beaches, roads, roofs, and fields turning a uniform grey. Some news reports describe the islands as looking moonscaped, a familiar term for surfaces that lose colour and texture under a thin coating of dust. Before and after satellite scenes make the change obvious. Greens dim, water surfaces darken, sharp edges blur. When ash falls, the immediate advice is simple but serious. Stay indoors and avoid breathing it. Volcanic ash is not soft like fireplace soot. It is made of tiny, hard, glass-like shards of pulverized rock. Inhaling it can irritate and damage lungs, especially for children, older adults, and people with respiratory issues. Ash also settles on catchments and open water supplies, changing the chemistry. Collection systems that feed household tanks or community cisterns can bring that contamination indoors. Clearing the ash from roofs and gutters becomes urgent, first to restore clean water and later to prevent structural load issues if more ash falls or if it rains. The loss of color is more than cosmetic. Plants need light. A thin ash layer blocks sunlight, dulling photosynthesis for days to weeks depending on thickness and weather. Leaves can clog and wilt. In the short term, crops and gardens suffer. Over longer spans, though, the same ash can aid recovery. Volcanic ash carries minerals, potassium, phosphorus, silica, trace elements that slowly weather and enrich soils. Many fertile regions on Earth owe their productivity to past eruptions. The near-term challenge is to bridge the gap between initial stress on plants and the later benefit to the land. Not all ash follows a horizontal path. The lightest, finest particles and droplets rose high with the main column and broke through into the stratosphere. Earth's lower atmosphere The troposphere is where weather happens, clouds, rain, and most day-to-day mixing. Above that, the stratosphere is more layered and stable. Vertical exchange between the two is limited, which means material that makes it into the stratosphere can linger for months to years. In addition to solid ash fragments, the eruption lofted gases that quickly formed aerosol droplets. The tiniest aerosols include sulfuric acid formed from sulfur dioxide, along with compounds like hydrogen sulfide and hydrochloric acid in smaller amounts. These droplets scatter sunlight back to space. On a global scale, if the injected amount is large and the altitude high, the result can be a slight temporary cooling of the planet's surface temperature. The effect depends on particle size, altitude, and how long the aerosols persist. It is a shade, not a switch. A cooling tendency does not mean the aerosols are a net positive. What goes up eventually returns. As particles grow and descend into the troposphere, they can be incorporated into raindrops. When that rain falls, acids that formed in the stratosphere come down with it, a process widely known as acid rain. The chemistry is complex and the amounts dilute, but over time and across regions, the deposition can affect lakes, soils, and built surfaces. For local communities, the more immediate concern is the ash that already fell, cleaning, restoring water quality, protecting airways, and assisting agriculture. One of the most remarkable features visible from orbit was the circular pressure wave racing outward from the blast. In infrared channels, which are sensitive to small temperature changes in cloud tops and the air itself, the wave looked like a series of bright and dark rings, each band marking slightly warmer or cooler air as the pressure pulse compressed and rarefied the atmosphere. This wave is a type of Lamb wave, an atmospheric disturbance that can travel long distances with little loss, hugging the surface. The front spread so quickly that observers described it as moving at or above the speed of sound in the surrounding air. Sound speed depends on temperature and altitude, but near the surface, it is roughly 340 meters per second. The pressure pulse wrapped the globe and was recorded on barometers far from the Pacific, sometimes multiple times as it circled. Where people were close enough to see the wave sweep past, the experience came with a loud, sharp report and then a drawn-out rumble as the air settled. Videos from islands about 65 kilometers away captured the passage. The camera frames show a normal seascape, then a sudden, low, horizontal haze line racing across the view, followed by a boom and a deep, rolling sound. The scale is easier to feel than to compute in those moments. Sound waves at that energy push against buildings and ears in a way that can be felt in the chest. Given the intensities, it is fortunate that injuries from the pressure alone were limited. Reports noted that eardrums remained intact in most places, which is notable considering the power of the blast. Even so, the shockwave carried enough energy to cause practical damage. In some communities, windows shattered as the front arrived, glass giving way to pressure differences and rapid air motion. Weather stations across the world caught the pressure signature as it went by. Sensitive barometers in the United States traced small, regular wiggles in air pressure as the wave arrived, weakened, and then returned again hours later from the opposite direction. The signal repeated as the disturbance lapped the globe. Analyses indicate it circled the Earth at least 4 times. The passage in most places was not something people could hear with the naked ear. What moved overhead was a broad pulse, spread over hundreds of kilometers, more like a slow global heartbeat than a sharp crack. Yet in some regions, the blast did cross the threshold of audibility. Reports came from New Zealand and Australia of a distant boom and rolling sound, and even from as far as Alaska. The difference is explained by how the atmosphere guides sound. Lower frequency waves, called infrasound, can travel very far with little loss, bending with temperature layers and winds. In a few places, those waves arrived with enough energy and under the right conditions to be heard. A separate question people asked quickly was whether this kind of event could trigger a tsunami. Most underwater eruptions do not. Typical submarine activity is slow compared to the speed at which ocean basins respond, and the vertical displacement of the sea surface is small. A tsunami needs the water column to be pushed or pulled on a large scale, either by a sudden movement of the seafloor, a fast landslide into the sea, or a rapid transfer of pressure. What happened at Hunga Tonga Hunga Ha'apai was unusual in both speed and size. The eruption produced a violent pressure pulse, likely drove a quick collapse in parts of the volcanic edifice, and forced a large column of water and air upward. The combination produced a tsunami, not a basin-wide giant, but one with enough amplitude to matter for coasts that faced the source. Even a modest tsunami changes the risk picture for harbors. When watches and warnings went out, many operators took standard action, moved boats and ships out of confined marinas into deeper water. Far offshore, a tsunami is a long, low wave that may only raise and lower the sea surface by a small amount. As it travels into shallower water near the coast, the wave slows. Energy is conserved, so the height increases and the wave steepens, making the rise more visible and the currents stronger. In narrow inlets and harbors, local geometry can amplify the motion further through resonance. Videos from the Pacific show boat crews turning bows into the surge to ride it safely, while in some ports, lines snapped, docks lifted and twisted, and smaller craft were tossed or grounded. The changes to the volcanic island itself tell a different, slower story about building and undoing land. The island that became known as Hunga Tonga Hunga Ha'apai was new. It first rose above the waves in 2014, created by eruptive activity at a site where two pre-existing island peaks, Hunga Tonga and Hunga Ha'apai, stood as the emergent rims of a large, mostly submerged volcanic structure. Between those older islands lay a caldera whose floor sat about 150 meters below sea level. When the 2014-2015 eruption began, ash, lapilli, and fragments piled up between the two islands, welding into a continuous stretch of land that bridged the gap. From space, the outline looked like a peanut with a dark, shallow lagoon in the middle. From the water, steep cliffs of layered ash and tuff showed where waves were already cutting in. The larger tectonic setting explains why this site is so active. The volcano sits near the line where the Pacific Plate and the Indo-Australian Plate converge. At convergent boundaries, one plate tends to dive beneath the other, a process called subduction. Water carried down with the sinking slab lowers the melting point of overlying mantle rock, producing magma that can rise through the crust. Many island arcs, including Tonga, are chains of volcanoes built by this process. The crust in such regions is fractured and dynamic. New vents can open, cones can form quickly, and islands can appear and erode in human timescales. Because the 2014 island formed in the ocean, where waves, rain, and spray act every day, it became a natural laboratory for erosion. NASA and partner scientists began to track it soon after it emerged. The goal was twofold. First, to understand how water reshapes fresh volcanic land on Earth over months to years. Second, to use that knowledge as an analog for conditions on Mars long ago, when parts of the Martian surface likely had standing lakes or shallow seas. Many volcanoes on Mars are ancient and now stand in dry, cold air, but their flanks and surroundings show patterns, channels, fans, layered deposits that hint at past interaction with water. Watching a new island's edges collapse, beaches form, and shorelines move lets researchers test which shapes are diagnostic of wave action, which of rainfall, and which of groundwater flow. At first, the island seemed fragile. The deposits were made largely of ash and fine fragments. Waves cut notches at the base of cliffs, and slabs fell away like pieces from a sand castle at the tide line. Gullies formed where rain carved paths down slopes, and the central lagoon connected to the open ocean through fresh breaches. Then, the behavior started to change. Over about 6 months, erosion rates slowed. The reason lies in the chemistry of volcanic ash. When ash interacts with seawater, it can transform into a tougher material. Minerals like palagonite form as glassy particles alter and cement together. The surface hardens, the edges become more resistant, and the island stabilizes. The new rock is still young and weak compared to old basalt, but it is no longer as easily swept away by every storm. If volcanic activity had stopped after that, Hunga Tonga Hunga Hahapai might have persisted as a low island for years or even decades, gradually lowering and smoothing as the ocean worked on it. The January 15 eruption reset the clock. The force of the event removed large sections of land, cut through the central area, and lowered the seafloor inside the caldera again. In satellite images after the blast, what had been a single stretch of emergent land reappeared as 2 separated remnants, aligned with the older islands, with open water between them. The central caldera floor, excavated and collapsed, dropped back below sea level. The processes that made the island the fast pileup of pyroclastic material were overwhelmed by the processes that can take it away in hours when circumstances align. Scale depends on the reference frame. From the vantage point of a ship or a beach, the vanished land seems small, a narrow link erased between 2 low islands. From the sea floor up, the structure is not small at all. The volcanic edifice rises thousands of meters from the ocean bottom. If Earth's oceans were somehow drained, the feature that now barely breaks the surface would stand as a mountain roughly 2 kilometers high. Underwater, much of the drama of construction and destruction is hidden. Only the hint at the top, the island we can see, tells us what is happening below. There is also the human perspective. For people living around the Pacific, the eruption's reach added stress and loss, even though the source was far away. It could have been worse under different conditions. A larger, deeper collapse can push more water. A closer source to a major coastline would leave less time for warnings. The size and shape of basins can focus waves. In this case, the tsunami heights were limited for most shores, and the pressure wave, while powerful, did not cause widespread injuries from overpressure. The damages that did occur, ash contamination of water systems, crop stress, broken windows, and harbor infrastructure, were significant but bounded. That does not diminish the power of the event. It shows how many factors control outcomes. For scientists and agencies, the island and its surroundings will remain a target of careful study. High-resolution satellites can follow changes in shoreline and bathymetry. Radar can see through clouds and ash to map surface roughness. Spectrometers can pick out mineral changes as fresh deposits alter in air and seawater. Ocean instruments can track how the eruption's materials disperse in currents and how the water column recovers. The data feed models that connect a volcanic blast to atmospheric waves, lightning, and aerosol formation, to ocean responses from tsunamis to turbidity plumes, and to ecological impacts on reefs and fisheries. Each piece helps fill a larger picture. There is a broader reason to pay attention. Eruptions of this scale couple Earth systems in ways that cross borders. They alter the upper atmosphere where satellites fly, changing drag and radio propagation. They inject particles that affect sunlight and cloud seeds. They move water and air in pulses that sensors can follow around the world. Understanding how those parts fit together improves warnings for aviation when ash is aloft, guidance for coastal communities when pressure waves and tsunamis are possible, and forecasts for climate effects when aerosols reach the stratosphere. The same knowledge helps us read the rock record on other worlds. On Mars, old volcanoes and dry basins preserve the footprints of water interacting with fire in a different time. By studying how a fresh island of ash hardened, eroded, and finally was cut apart by a single great event, and by measuring how its plume charged the sky and stirred the sea, we gain a clearer view of how planets behave. Volcanic activity at this scale can have global impacts, and by studying their interactions with the atmosphere and oceans, we not only can help predict our futures, but understand the past on planets like Mars. Enceladus is small by almost any measure, yet it draws attention from across planetary science. It is only the 6th largest moon of Saturn. In sunlight, it looks plain, smooth, bright, and almost featureless from far away. That first look can be misleading. Beneath the calm surface, this world is active. Its south polar region sends out continuous jets of water vapor and fine ice, rising from long cracks that slice the crust. In image after image, you can see thin curtains of spray against space. The contrast between a simple exterior and busy interior is what makes Enceladus so compelling. Much of what we know comes from the Cassini mission, which orbited Saturn from 2004 to 2017. Cassini flew by Enceladus many times at different distances and angles. It carried cameras that could spot tiny plumes, spectrometers that could read the composition of gases and grains, and instruments that felt slight tugs in gravity to infer mass inside the moon. With this set of tools, a small, cold satellite turned into a laboratory for active geology and possible habitability. In some ways, we have finer detail for Enceladus than for some larger, closer moons elsewhere, simply because Cassini returned often and kept watching as patterns repeated. To place Enceladus in context, start with its path around Saturn. Among the planet's many moons, it is currently counted as the 14th closest in mean distance to the planet. Currently matters because Saturn hosts tiny moonlets inside the rings. Some get discovered, reclassified, or lost in data until orbits are confirmed. Among the major moons, the larger named body's Enceladus is the second closest, just outside Mimas. That location means the moon orbits just beyond the main rings, yet stays in the same broad plane. Its orbit lies in the ring plane with only a small tilt, so from certain vantage points it seems to skim right along the ring edge. A circuit around Saturn takes only about 33 hours. You could think of that as a very short month on Enceladus, with days and nights changing over a little more than one Earth day. Enceladus also keeps time with a neighbor. It is in a 2-to-1 orbital resonance with Dione, another of Saturn's mid-sized moons. A resonance is a simple ratio in orbital periods. In this case, Enceladus goes around twice for each single orbit of Dione. The importance is not the number itself, but the result. The gravitational tugs line up at regular intervals. Those repeating pulls prevent Enceladus's path from relaxing into a perfect circle. The orbit stays slightly stretched, or eccentric. When a body moves on an eccentric path near a massive planet, it gets squeezed and relaxed with each lap. That squeeze is called tidal deformation. Rock and ice flex, and as they flex, they warm. The energy that goes into bending the body is turned into heat deep inside. Surface makeup controls how that heat expresses itself. Measurements from Cassini show that the surface of Enceladus is made almost entirely of water ice. Clean here means there is very little rock or dark dust mixed in. With few impurities to absorb sunlight, the surface returns most of the incoming light back to space. Scientists describe that with bond albedo, a fraction that runs from 0 to 1. Enceladus has a bond albedo around 0.81, about as reflective as fresh snow. A highly reflective surface stays cold under the distant Sunday noon temperatures. On the open plains, hover near 200 degrees Celsius. At that temperature, water is hard and brittle. Most processes we associate with liquid water cannot happen at the surface. Inside, the picture changes. Ice is not uniform from the top down. Pressure rises with depth, and tidal heating is stronger in certain layers. Models and measurements point to an ice shell, roughly 30 to 40 kilometers thick, above the South Polar region, and possibly similar or somewhat thicker elsewhere. Below that shell lies liquid water. The simplest way to say it is that Enceladus is a frozen ocean world, a solid ice crust on top, a liquid layer beneath, and a rocky core deeper down. The analogy many people use is Earth's crust above a mantle of soft, hot rock, except here the roles are played by ice and liquid water. Whether the ocean is truly global or concentrated toward the South Pole is still under study, but the evidence is strong for at least a large, long-lived sea beneath the South Polar terrain. How do we know liquid is there? The jets are the most obvious clue. At Enceladus's South Pole, 4 long fractures, nicknamed tiger stripes, run roughly parallel and pour out water vapor, ice grains, and trace molecules. This is cryovolcanism. Cryo for cold, volcanism for material venting from the inside. Instead of molten rock, the vents release water and volatile compounds. Cassini flew directly through these plumes multiple times. It measured the speed of particles, the mass of material, and the chemistry of both gas and grains. Typical flow rates are around 250 kilograms per second, about the mass of a small car every second spraying into space. The jet speeds exceed 2,000 kilometers per hour, fast enough that many molecules escape the moon's weak gravity instead of falling back as snow. Those escaped particles do not simply disappear. Enceladus orbits within Saturn's broad ring system, just outside the main bright rings. The tiny grains and vapor released from the South Pole spread out along the orbit and feed one of Saturn's faintest structures, the E-ring. Unlike the dense A and B rings, the E-ring is a very diffuse torus of fine ice particles that extends for millions of kilometers. It is so thinly populated that, to our eyes, it becomes striking only when sunlight strikes from behind. Backlighting turns a sparse haze into a bright sheet, and the ring shows itself as a pale halo around the planet. In this way, a small moon maintains a large ring. Jets release water, particles drift outward, and the system keeps renewing itself. The brightness of Enceladus also helps instruments find warm places. Against a very cold, white background, even small rises in temperature stand out in infrared data. Cassini mapped narrow strips along the tiger stripes that were warmer than their surroundings, still far below freezing in human terms, but warm enough to hint at vents and underlying channels. Gravity measurements during close passes showed slight variations expected if denser or lighter materials lay beneath, again pointing to a liquid layer interacting with the crust. Tiny wobbles in Enceladus's rotation, a property called libration, also fit best if the crust is mechanically decoupled from the core by a global ocean. Taken together, these lines of evidence, jets, heat, gravity, and motion build a consistent picture without needing to dig. The resonance with Dione remains at the center of the heat story. Without that regular pump, the interior would cool and the crust would likely thicken until vents closed. With it, stress keeps working the shell and the rocky core. The ice near the tiger stripes fractures repeatedly. Those cracks act like valves that open and narrow as tidal stress cycles, letting more or less material out. Observations across different times in Enceladus's orbit show the plume brightness rising and falling, a sign that the jets respond to the squeeze as expected. In a way, the moon breathes, the crust flexes, vents widen, water vapor flows, then the system relaxes and output dips. Composition adds to the interest. Cassini's mass spectrometer tasted more than water. The gas contained simple molecules like carbon dioxide and methane, along with ammonia and traces of organics, carbon-bearing compounds. The ice grains carried salts and silica particles that likely formed where liquid water interacts with rock at the seafloor. On Earth, such interactions occur at hydrothermal vents, where heated water moves through cracks in the crust and leaches minerals from rock. The presence of salts and nanometer-scale silica grains in Enceladus's plumes hints at warm water meeting rock below, a key ingredient for chemical energy. The focus here remains on the physical picture, a subsurface ocean in contact with a rocky core, stirred by tides, venting to space along polar cracks. The surface, meanwhile, tells a story of youth and renewal. Enceladus's plains are bright and relatively smooth, with few impact craters compared to older, darker moons. Ridges and grooves cross in clean patterns, as if the ice has been reshaped and resurfaced many times. Fresh snow from fallout near the South Pole coats the ground. Where older terrains do appear, they are often softened by later deposits. The high albedo keeps the temperature low, which preserves sharp edges in the cracks, but also prevents heat from spreading laterally very far. All of these features, fast orbit, resonance with Dione, tidal heat, clean ice shell, liquid water beneath, active vents tied together. The small size and high reflectivity explain the cold exterior. The orbital mechanics explain the interior energy. The mechanical behavior of ice explains how fractures can stay open and deliver vapor to space without the surface melting into puddles. The weak gravity explains how easily grains can escape, and the connection to Saturn explains why the E-ring stays present year after year even though individual particles are lost over time. When backlit by the sun, that ring appears, faint but wide, a visible reminder that a moon only a few hundred kilometers across can shape a structure larger than Saturn itself. Seen from a slant, the sunlight that slips through the finest ice grains around Saturn makes one ring glow an intense, clear blue. The effect is most striking when the particles are small and the lighting is right. so the ring scatters shorter wavelengths toward the viewer. Among solar system features, this makes Saturn's E-ring look unusually blue, more uniform, and more sharply tinted than the soft aquas we associate with Neptune's clouds. The E-ring sits far from the bright main rings, a broad, faint band on the system's outer edge in classical naming. Its size is not obvious to the eye. It is a diffuse sheet of material, spread across a huge radial span, measured in thousands upon thousands of kilometers, and its form is guided strongly by the path of the small moon that feeds it. That moon is Enceladus. Each time its south polar vents release water vapor and ice grains, the new material does not just vanish. Some grains fall back like snow, but much of it escapes and drifts into the ring, because the jets are not steady fire hoses, but instead vary with the moon's tidal flexing and with local fractures opening and narrowing. The fresh material sometimes lays down in streaks. In images taken at shallow angles, you can trace tendrils, narrow structures that extend and curl within the ring, marking where plumes have recently added new grains. As Enceladus moves along its orbit, solar radiation, plasma, drag, and collisions among grains tend to level out those structures. What starts as distinct filaments gradually smooths into the E-ring's background haze until the next strong burst writes a new set of lines. Cassini's tour through the Saturn system gave scientists a rare chance to sample these materials directly. The mission was never conceived around flying through icy jets. When Cassini launched, the existence of active plumes on Enceladus was unknown. Yet the spacecraft carried an instrument that turned out to be ideal for tasting tiny solids, the Cosmic Dust Analyzer, CDA. CDA was built to measure the size, speed, and composition of micrometer-scale grains in Saturn's neighborhood ring particles, interplanetary dust, and the like. When Enceladus's activity became clear, mission planners threaded Cassini through the plume at safe speeds and angles so the instrument could register impacts from fresh grains. Because CDA was optimized for dust and not for sampling gas, and because the geometry of each pass was limited by spacecraft safety, the readings cannot capture every compound with perfect completeness. Even so, the results were unambiguous about the main ingredients. Water dominated, as expected for a world venting from an icy shell and a subsurface sea. Mixed into and onto those ice grains were other species: carbon dioxide, methane, nitrogen-bearing compounds, ammonia, and a suite of organics. Some detections suggested simple organics and potential precursors to amino acids, the kinds of carbon-based molecules that, on Earth, take part in pathways that lead toward biology. Finding such building blocks is not the same as finding life. It does, however, show that the chemistry in and around the ocean includes ingredients that, in our experience, can support complex reactions. The gas phase told its own story. Other instruments measured water vapor streaming out alongside the ice grains, with trace gases that change in proportion as the vents open and narrow over the course of Enceladus's orbit. The mix hints at temperature and pressure conditions below the ice and at how the liquid interacts with rock. Over multiple flybys, Cassini also detected molecular hydrogen, H2, in the plume. Hydrogen can form when hot water reacts with certain minerals, a process known on Earth as serpentinization. On our ocean floors, where seawater circulates through hot rock at hydrothermal vents, these reactions produce hydrogen, methane, and a buffet of dissolved chemicals that microbial life can use as energy sources. The parallel is not proof of vents on Enceladus, but it points in that direction. water in contact with rock at elevated temperatures, exchanging and creating gases as it moves. Questions about the interior shape the next set of inferences. Early in Cassini's mission, some models treated Enceladus as if it might be largely ice throughout, a simple cold ball with a warm pocket near the South Pole. As gravity data accumulated and the spacecraft tracked tiny changes in the Moon's motion, that picture grew more complex. The measured mass and the way mass is distributed require denser material deep inside. If Enceladus were pure water, even with a liquid layer, the numbers would not match. The most straightforward way to reconcile the measurements is to give Enceladus a rocky core silicate and perhaps some iron-bearing material beneath its global or near-global ocean. When scientists say a small world is differentiated, they mean its interior sorted itself into layers. Heavy materials sank, lighter materials rose, and over time, those layers became distinct. Differentiation requires enough heat and time for materials to flow, at least slowly. Enceladus is a borderline case by size. At about 500 kilometers across, it sits near the lower end of objects that we expect to relax into near-spherical shapes under their own gravity. Many bodies this small are irregular, like asteroid Lutetia or Neptune's moon Proteus, which resemble lumpy potatoes more than smooth spheres. Enceladus, by contrast, is round enough to suggest that gravity has smoothed it and that inside it had sufficient energy to let materials move relative to one another. Differentiation gives Enceladus a structure that looks sensible in light of everything else we observe: a rocky core at the center, an ocean layer above that, and an ice shell on top. The core's rock provides more than mass. It is the substrate against which water can react, the scaffolding for hydrothermal systems, and the source of many of the dissolved ions and minerals we see locked into plume grains. Tidal heating concentrates near the boundaries between materials at the interface where ice meets ocean and where ocean meets rock, because those layers deform differently under stress. Cracks open in the ice shell where stress is high, especially near the South Pole, where the shell appears thinner. Those cracks become conduits. In the ocean, water circulating through a porous or fractured rocky core can pick up heat and chemicals, then rise and vent as part of a convective loop. The blue glow of the E-ring, beautiful as it is, doubles as a tracer of these processes. Fresh ice grains are bright and scatter light in a way that picks out shorter wavelengths. Over time, sunlight and charged particles darken and alter ring particles, so the bluest regions are often where new material joins. Observing the E-ring's color gradients, thickness, and brightness over a Saturnian year gave researchers a way to map not only where Enceladus orbits, but how steadily it feeds the ring. When the plumes are strong, the ring brightens and shows more fine structure. When they dip, the ring grows more uniform again. It is a planetary scale ledger of a moon's breathing. On the surface of Enceladus, the feedback loop is visible in textures. Near the tiger stripes, freshly fallen frost coats the ground in bright streaks and patches. Thermal maps show narrow, warm lanes along the fractures, with temperatures declining rapidly away from the vents. That pattern implies heat is being delivered from below through well-defined channels, not smeared broadly across the crust. In places where fractures cross, the activity can be especially complex. Multiple jets, overlapping deposits, and small mounds formed by reworked snow. All of it sits under a sun so distant that no liquid water stays at the surface. The motion is internal. The surface is the canvas. Returning to the interior, the case for a rocky core is strengthened by mass and by context. Saturn's moons likely formed from a mix of ice and rock, with proportions set by the temperature and density of the protoplanetary disk in that region. Even if Enceladus began with a high fraction of ice, the observed density today cannot be explained by ice alone. A rock-rich core is the natural answer. That core matters if we imagine hydrothermal vents. On Earth, these vents form where seawater percolates through hot rock, heats up, reacts, and then exits back into the ocean through chimneys or diffuse flows. The fluids carry dissolved minerals, gases, and tiny particles of silica that precipitate as they cool. Cassini saw salt-rich grains and nanometer-scale silica particles in Enceladus's plume signatures that point toward warm water meeting fresh rock somewhere at depth. The notion that Enceladus might once have been water all the way through reflects how open the early questions were. With limited data, it was reasonable to test extremes: a mostly icy sphere versus a layered Earth-like mini-world. Each new pass tightened the constraints. Gravity measurements refined the interior mass distribution. Libration studies showed that the shell and the core do not behave as a single rigid piece, a clue that a decoupling layer and ocean must lie between them. Thermal measurements tied warm stripes to the precise locations of fractures seen in images, and plume sampling tied the chemistry to interactions with rock. Taken together, the weight of evidence now leans toward a differentiated interior with a predominantly rocky core. Size remains a useful reminder of how remarkable this is. Enceladus is small enough to test the limits of what gravity can round. It is small enough that without a tidal engine it would have frozen solid long ago, its interior heat lost to space. It is also active enough to keep a ring supplied, to vent hundreds of kilograms per second into space, and to draw a visible signature in Saturn's environment every day. That combination, small, bright, cold outside, layered, warm, and dynamic inside, makes it a prime laboratory for understanding ocean worlds. If the core is rocky, the ocean does not sit on a featureless floor. It lies on fractured, reactive material that can supply and recycle chemicals. That kind of seabed matters for energy and for nutrients. As water moves across hot rock, it can pick up dissolved minerals such as sodium, potassium, calcium, and silica, and it can generate gases like hydrogen through rock-water reactions. On Earth, ecosystems thrive around such vents without sunlight, using chemical gradients as fuel. No one has seen Enceladus's seafloor, and life has not been detected there. But a rocky ocean floor would provide pathways for circulation, sites for mineral exchange, and a palette of elements and compounds that, by our best current reasoning, are essential for what we believe life would need to form and evolve. Thermal activity on Enceladus is not a guess. It is built into the way the moon behaves. The plumes exist because heat is moving from the inside to the outside, opening and sustaining vents. When Cassini crossed the South Polar region, it mapped the heat coming from the surface and found that the warmest lines matched a set of long, dark trenches. These features are now called the tiger stripes. Each one is a giant depression about 130 kilometers long, roughly 2 kilometers wide, and around 500 meters deep. The scale is large enough to span a small country, yet the edges are sharp and clean, as if someone scored the ice with a blade. The leading idea is that these are tectonic fractures in the ice shell faults that open and close slightly as tides flex the crust. The surface patterns around the tiger stripes explain why the South Pole looks so fresh. Across that hemisphere, there are almost no impact craters at all, and even away from the pole, craters are scarce. In the solar system, A lack of craters usually means young ground. Old surfaces collect scars. Young surfaces are resurfaced before new craters can pile up. Enceladus does not carry a thick atmosphere that could burn up small space rocks before they strike. The air that surrounds it is a thin shroud made mainly of water vapor blown out by the plumes. It has too little mass to shield the surface. Instead, the youth comes from constant renewal. Snow from the plumes falls back as bright frost. Fine particles drift down and smooth rough places. Over time, that soft rain of ice rounds the landscape and fills shallow pits. This steady smoothing is one reason Enceladus is so round for a body only about 500 kilometers across. Small objects often look lumpy because their gravity is not strong enough to pull them into a near sphere. Enceladus approaches a smooth figure because gravity has done its work, and because later resurfacing has erased many of the bumps. Outside of the big fractures and a handful of older craters, topographic relief is modest. There are no mountain chains stretched across the globe. If you zoom far in near the South Pole, you find what could be called rough terrain ridges, pits, and hummocks that speak to local stress, but even these forms sit low compared to mountains on bigger worlds. High-resolution images show a skin that resembles a giant glacier, bands, folds, and slabs, with textures that switch from polished to jagged over short distances. In the north, the face changes. Craters become more common, and fractures, while present, do not host active vents. Without plumes to paint the ground and fill the lows, the northern terrains preserve more of their history. This makes the North Pole older, by inference. It is not that tides ignore the north. It is that the thin shell and organized vent system are concentrated in the south. In that polar province, Cassini took its closest looks. Flying through the plume was risky, but possible. Engineers threaded the spacecraft to minimize dust hazard. Then instruments scanned the surface and the jets. The results from those passes gave us crisp views of the tiger stripes and the surrounding fields of fall. The texture near the stripes is unlike any ice on Earth. Lines cross and fork, as if the surface has been folded, squeezed, and slid sideways over and over. In places, the ice appears to have been pulled apart and then welded shut. Some ridges look like frozen waves. Others look like rafts that broke loose and refroze in a slightly new arrangement. This record fits an ice shell that opens and narrows in a tidal rhythm and a heat source that weakens the shell from below. Warmth travels up narrow channels, not as a broad blanket, where the stress is highest and the shell thinnest. The cracks stay alive, breathing water, vapor, and grains. Getting any of these images was a technical accomplishment. Enceladus orbits inside a system rich in charged particles, dust, and gravitational nudges. Cassini had to balance safety with science, adjusting speed and angle to pass through the plume without damaging its instruments. Even so, the mission delivered repeated, targeted flybys. With its end in 2017, that window closed. Today, no spacecraft orbits Saturn, so there is no platform on site to keep watching Enceladus as it changes with time. Proposals have come and gone for new missions: a dedicated orbiter, a lander, a plume sampler with more capable mass spectrometers, but none have flown yet. The wish list is long. The most direct experiment would be to reach the ocean. That could mean melting or drilling through tens of kilometers of ice, a monumental engineering task. Short of that, a mission could fly again through the plumes with instruments designed specifically for biosignature detection, high-resolution mass spectrometers to separate complex organics, microscopes to look for cell-like structures in ice grains, and sensors tuned to measure tiny variations in isotopes. Plume particles are ejected straight from the ocean and from its boundary with the core. Sampling them is the next best thing to sampling the ocean itself. Even a series of repeated flybys at different points in the orbit could reveal how vent output, chemistry, and heat vary with stress. While Enceladus waits for its next visitor, other work continues in the Saturn system. A mission named Dragonfly is headed to Titan, another moon of Saturn, with a thick atmosphere and organic-rich dunes. Dragonfly is a rotorcraft that will fly through Titan's air and land at multiple sites to study complex chemistry on the surface. It will not explore Enceladus, but what it learns about organics and energy in a cold environment may help frame questions for ocean worlds. Separately, a few proposals that target Enceladus are under review. They range from orbiters that could map the ice thickness and gravity field in detail, to flyby craft that could taste plumes with instruments a generation beyond Cassini's. Such missions take years to plan and build, then years to cruise. Even with approvals, we are likely many years, possibly decades away from answers that require new in-situ data. The pause does not erase what we have. Cassini's maps of thermal emission pin the tiger stripes as active conduits. The jets and their chemistry point to liquid water in contact with rock. The gravity and rotation data favor a global or near-global ocean under a shell that thins toward the south. The near absence of craters in the south and the wide blanketing of bright frost tell us the surface there is geologically young. Taken together, these lines point toward a differentiated interior with a rocky core. That core would be the floor of the ocean and the site where hydrothermal systems could form. The same places that produce salts and tiny silica grains could produce molecular hydrogen and other reduced compounds, which serve as energy sources for microbes on Earth. The chain of reasoning is careful. Liquid water plus heat plus rock-water chemistry equals potential habitats. It does not claim more than that. It sets the stage for a better search. Even the shape and cleanliness of the ice carry information. Because the surface is made of almost pure water ice, it reflects most sunlight and stays extremely cold. That cold preserves fractures and subtle relief without letting them flow away quickly. It also means any liquid must reach the surface from below and then freeze fast, so vents supply vapor and grains rather than streams. The simplicity of the surface composition helps instruments read temperature contrasts and chemical hints. Over time, fine grains settle back from the plume and patch the ground, resetting the clock for crater counts and covering small scars. The tiger stripes remain the key. Their dimensions, 130 by 2 by 0.5 kilometers, imply deep roots in the shell. Their warmth implies open pathways. Their alignment and spacing suggest stress fields that repeat over broad areas. In some flybys, Cassini measured brighter plumes when the moon was at a place in its orbit where tidal stress would be expected to pull the fractures open. At other points, when compression should dominate, the plumes dimmed. This phase locking strengthens the case that the fractures are not relics of a past event, but are living features, modulated by the daily forcing of Saturn's gravity. Directly above them, fine snow falls almost continuously, leaving fans and streaks that drift with light winds and local topography. Because the south is young and the north is older, Enceladus offers 2 time windows at once. The south shows processes working now. The north stores the quieter record of impacts and slow deformation. Comparing the two helps researchers separate short-term activity from long-term background. It also shows how even a small body can divide into distinct provinces when internal heating is focused in one region. That division may shift over geologic time. If the shell thickens or stress patterns change, different bands could become active. For now, the South Pole is the engine. The absence of a new spacecraft makes creative uses of old data more important. Teams still reprocess Cassini images for better resolution. They stack multiple frames to boost signal in faint plumes. They refine gravity inversions to sketch the shape of the core and the thickness of the shell. They run lab experiments to see how ice grains acquire salts and organics, then compare those spectra to what Cassini's instruments saw in flight. All of this builds confidence in the interpretation, while setting clear targets for the next generation of sensors. From this world of ice and hidden water, the story shifts to a very different kind of moon. Triton is exceptional and easy to overlook. It carries a list of features that make it stand apart. A retrograde orbit, a likely captured past, icy geology that hints at activity, and a thin atmosphere with nitrogen frost. It is also the largest moon of Neptune, the planet farthest from the Sun, which makes it hard to reach. We have visited it only once, and only briefly, when Voyager 2 swept through the Neptune system in 1989. That single pass, more than 30 years ago, gave us a first and fleeting look. Voyager 2's brief pass showed that Triton is not a typical outer moon. It sits inside a system with 14 known moons, yet it behaves more like a world that arrived from far away and settled into a special place. To see why, start with how Neptune's moons are grouped. The 7 inner moons are called regular because they circle close to the planet in the same direction Neptune spins, their paths lying nearly in the planet's equatorial plane and their orbits close to circular. Past those, the pattern breaks. The next set are irregular moons. Their orbits can be tilted, stretched, and sometimes run backward compared to the planet's rotation. Triton is the first of these irregulars, and it is the largest by far. Its path is the giveaway. Triton orbits Neptune in a retrograde direction. It goes clockwise as Neptune's rotation goes counterclockwise. That is the opposite of what we see for all the other large moons in the solar system, which travel in the same direction their planets spin. Triton's orbital plane is also tilted steeply. If you could lay Neptune's equator flat on a table, Triton's path would be tipped up at about 130 degrees to that plane. In simple terms, it is not following the traffic flow. At the same time, its orbital eccentricity, how stretched the orbit is, sits close to zero. The path is nearly a perfect circle, even though the plane is highly inclined and the direction is backward. That mix of properties is unusual and important. A retrograde, highly inclined, nearly circular orbit points toward capture rather than local birth. Capture means Triton did not form beside Neptune, inside a disk of gas and dust around the young planet. It likely formed in the distant, icy zone beyond Neptune, the Kuiper Belt, and only later was pulled into Neptune's gravity well. The leading idea for how that could happen uses a binary origin. Imagine Triton not as a lone object, but as one half of a pair, like Pluto and its large moon Charon. When such a binary passes near a giant planet, tidal forces can stretch and rotate the pair. Energy and momentum are exchanged. In some encounters, one member is flung away at higher speed, while the other loses energy and becomes bound to the planet. For Triton, the scenario goes like this. It once orbited a partner at Kuiper Belt distances. The binary wandered near Neptune. The encounter broke the pair. Triton shed enough energy to be captured, while its partner was thrown outward or inward on a new path. Over time, friction from tides within Triton and within Neptune then rounded Triton's captured orbit into the nearly circular track we see today. Once captured, Triton quickly became the dominant body in Neptune's satellite system. By mass, it makes up about 99.5% of all the material orbiting Neptune. The other moons are small. In relative terms, only the Earth-Moon pair shows a larger share of mass in the main moon compared to the rest of its system. Triton's absolute size adds more context. It is the 7th largest moon in the solar system. It is smaller than Earth's moon, Ganymede, Titan, Callisto, Io, and Europa, but it is larger than any other satellite. It also exceeds Pluto in diameter and mass. That comparison matters for origin stories. Pluto has long been seen as one of the largest native objects of the Kuiper Belt. Triton's greater size and its likely origin in the same reservoir mean that a world at least as large as Pluto was removed from that population and placed around Neptune. From a formation point of view, you can think of Triton as the biggest Kuiper Belt object we can study up close, just one that no longer lives in the Kuiper Belt. Apparent size in the sky depends on distance as well as true size. Triton orbits Neptune more closely than our moon orbits Earth. So even though Triton is physically smaller than our moon, it can look similar in angular size from Neptune's cloud tops. A disk about the same apparent width drifts across the planet's sky. That helps scientists scale images and plan occultation observations, where a moon passes in front of a star and the starlight cuts through the moon's thin atmosphere. Evidence for Triton's kinship with Pluto is not just logic from dynamics, it is also chemistry. Pluto's surface, mapped in detail by New Horizons in 2015, is dominated by nitrogen ice with patches of methane and carbon monoxide, plus water ice as a tough bedrock under those volatile layers. Triton's surface is similar, a cold veneer made mostly of nitrogen, with other ices mixed in, including methane, carbon dioxide, and water. When New Horizons returned compositional maps of Pluto, the match in major components supported the idea that Triton and Pluto share a common heritage. They formed in the same cold storehouse of ices and rock, and the same volatile species froze out onto their surfaces. Triton's presence also seems to have shaped the rest of the Neptunian system. Beyond its orbit, 6 other irregular moons circle far out on long, stretched, and tilted paths. These small bodies are almost certainly captured as well. Their current orbits may have been nudged by Triton's gravity as the system settled after the capture. In models, the sudden arrival of a heavy retrograde moon can disturb existing satellites, eject some, and tilt or stretch the orbits of others. The result is a family portrait with one massive, backward-moving moon and a scatter of much smaller, oddly inclined ones beyond. The capture story raises a key physical point. A body must lose energy to be caught. A lone object on a hyperbolic or highly elongated path has too much speed to remain. It will fly past and continue on. 3 main mechanisms can lower that energy. One is gas drag, but by the time Neptune's main disk of gas was gone, the drag would have been weak. The second is a direct collision, which is unlikely for large bodies. The third is a gravitational interaction with more than one moving mass, like a binary encounter. That last option has become the favorite because it is efficient and consistent with what we see in the Kuiper Belt today. Many binaries of different sizes, including Pluto-Charon. In such an exchange, one body is ejected with added energy, and the other loses energy and stays. Triton's surface relief is gentle. Voyager 2's images showed that, across wide areas, the height of the terrain does not vary by more than about a kilometer. That is a very flat world by outer planet standards. Even so, flat does not mean featureless. The spacecraft saw plateaus and plains, long ridges and troughs, and strange patches where the ground looks like it has been smoothed and then cut by intersecting lines. Some areas resemble frozen lakes of slushy nitrogen or water ice that later fractured. Others look like sheets broken into polygons and rotated slightly. Overprinted on these are terrains marked by low mounds and dark streaks, signs that some process has been at work from below. One of the first surprises was the scarcity of impact craters. Old surfaces collect craters over time, and without an atmosphere thick enough to burn up small bodies, an inactive world should show a record of many strikes. Triton does not. The few craters that do exist cluster in certain regions and appear modified. That pattern implies a surface that is young in many places. It has been resurfaced by geologic processes that erase or soften older scars. Resurfacing can happen when fresh ices flow slowly like glaciers, when materials vent from below and settle as new layers, or when frost cycles paint the ground over and over. On Triton, several of these processes may be active. The lack of craters tells us the clock has been reset across wide areas within geologically recent times. Color adds another piece. Triton carries reddish patches in some regions. A likely source is Tholin's complex organic residues produced when simpler molecules like methane and nitrogen are exposed to ultraviolet light from the sun or to energetic particles in space. In lab experiments, those inputs drive chemical reactions that build long, carbon-rich chains and rings. The resulting material is dark and reddish-brown, with a tar-like sticky quality. Tholins are not alive. They are not even a single compound, but rather a family of products that form under a range of conditions. Their presence is important because they represent a step between very simple ices and more complex organic chemistry. On icy bodies, tholins can coat surfaces, tint ices, and change how light is absorbed and reflected. The thin atmosphere over Triton interacts with these surface materials. It is made mostly of nitrogen, with traces of methane and other gases. The pressure is tiny compared to Earth's only a few tens of microbars near the surface, but it is enough to allow frost to sublime and recondense with the seasons. As Triton moves around Neptune and Neptune moves around the Sun, sunlight shifts across Triton's poles and equator. Nitrogen frost can evaporate from sunlit regions and settle onto colder ones, moving mass and smoothing terrain. This cycle, slow but steady, helps maintain the low relief and can hide older marks. It also supports winds strong enough to push fine particles into streaks and waves, the kind of patterns Voyager 2 recorded. When scientists say Triton's orbit is irregular, they are naming a set of linked traits: high inclination, retrograde motion, and a history that points away from local birth. The nearly circular shape of the orbit today does not contradict capture. After Triton was caught, tides did the rest. A large moon in a close retrograde orbit raises tides within Neptune and within itself. The friction from those tides converts orbital energy into heat and slowly reshapes the path. Over long spans, the eccentricity drops while the inclination and retrograde sense remain. What we see now is the end state of that damping, a round path in a tilted, backward plane. Size comparisons help anchor the mind. Triton's diameter is about 2,700 kilometers. Pluto's is about 2,380 kilometers. Our moon's is about 3,474 kilometers. So Triton sits between Pluto and the Moon in bulk. Because it orbits closer to Neptune than the Moon orbits Earth, it looms large in Neptune's sky, even though it is physically smaller. If you stood on a hypothetical platform in Neptune's upper atmosphere, Triton would show a disk not far off the apparent size of our Moon from Earth. The comparison is useful because it tells you how often occultations can be seen and how strong Triton's tides might be on the planet. Composition links back to origin again. A surface of nitrogen ice with patches of methane and carbon dioxide points to a very cold world with a supply of volatile molecules. Water ice provides the strong framework underneath. Over time, sunlight can drive methane to break apart and reassemble into heavier organics, the tholins that create red patches. The same processing can darken areas and change how quickly they warm in sunlight, which feeds back into where frost forms next. New Horizons data on Pluto showed this cycle in action: bright nitrogen plains, darker methane-rich areas, and complex seasonal transport. Triton appears to be running a similar system at a different distance and under different orbital constraints. The comparison to Pluto extends to structure. Both bodies likely have rocky interiors overlain by thick shells of water ice with volatile ices on top. The density of Triton tells us it cannot be pure ice. There must be a significant rock fraction. That mixture matches expectations for large Kuiper Belt objects that formed from a blend of dust, rock, and ices in the cold outer disk. If captured, Triton carried that composition with it. Afterward, heating from radioactive decay and tides may have altered the interior. Some models even allow for past or present internal oceans of water mixed with ammonia, which lowers the freezing point. Voyager 2 did not have the instruments to confirm such layers, but the possibility adds to the case for ongoing activity on the surface, since internal heat plus volatiles can drive vents and flows. Triton's surface smoothness raises another practical point. Many of the features are subtle and require close, well-lit imaging. Voyager 2's cameras, while excellent for their time, had limits in resolution and coverage during a fast flyby. We saw only one hemisphere in detail and only under one set of seasonal conditions. That is why the lack of craters and the presence of odd textures stood out so strongly. Even in a small sample, the signs of youth and reshaping were everywhere. Later ground-based and space-based observations refined the orbit and hinted at changes in the atmosphere over years, but nothing since 1989 has matched the spatial detail from up close. Putting all these parts together, retrograde, inclined, nearly circular orbit, mass dominance, Pluto-like chemistry, young, low-relief terrains with few craters, reddish tholin patches, a thin nitrogen atmosphere, you get a coherent view. Triton is almost certainly a captured dwarf planet from the Kuiper Belt that now rules Neptune's moon system. Its surface is active enough to refresh itself. Its composition matches its suspected birthplace. Its path and size explain its effects on other small moons, and its colors hint at ongoing chemical processing under weak sunlight at the edge of the solar system. Organic chemistry on Triton is a topic of careful wording. Tholins and other carbon-bearing materials are present, likely produced when methane and nitrogen are broken and rebuilt by ultraviolet light and energetic particles. These are not signs of life. They do show that the raw ingredients for more complex chemistry are available. On Earth, and in laboratory settings, simple molecules exposed to energy can build into larger chains and rings that, with the right conditions, become part of the chemistry that life uses. That is the context in which organic is used here. Carbon-containing compounds formed by natural processes on cold surfaces. Organic compounds do not mean life is present there. Organic compounds are the basic chemicals from which life forms. Life on Triton would not survive at the surface. The sun is far too dim there, and the air is far too thin and cold for any known organism to carry out the chemistry it needs. The interest shifts below the crust. Models and measurements point to a dense interior made of rock and metal. That mix gives Triton a relatively high bulk density for an icy moon, about 2 grams per cubic centimeter, much heavier than a body of pure water ice. Because of this mass, and because there is a big gap down to the next largest Uranian moon, Titania, Triton alone outweighs all the smaller moons in the solar system combined. The rock inside is not just ballast. Radioactive elements in rock release heat as they break down. Over long spans, that heat, together with tidal flexing in the past, could drive slow convection and keep part of the interior warm enough for liquid water to exist beneath the ice. If such a subsurface ocean is present, it fits a pattern seen at Europa and Enceladus. Liquid water trapped under an ice shell, exchanging heat and chemicals with a rocky base. On Triton, signs at the surface suggest that cryovolcanism, cold volcanism, has refreshed the ground in geologically recent times and may still be active. In cryovolcanism, the magma is water mixed with other volatiles like ammonia or nitrogen. It rises through fractures, erupts at or near the surface, and freezes into new layers. This steady resurfacing explains why Voyager 2 saw so few impact craters. Old marks are buried or softened by fresh deposits. Some of the smooth, sparse plains look especially young. In places, those plains are encircled by low rims, as if they were once open ponds that filled to the brim and then solidified. A solidified cryolava lake behaves like a frozen planitia, a flat-floored basin with raised edges that hold the cooled material in place. Elsewhere, Voyager 2 imaged broad, shallow depressions that resemble calderas, collapse pits formed after material drains from an underground source. Those calderas are natural outlets for cryolava, and their floors feed the smooth plains nearby. Erupting fluid would not rise alone. It would carry dissolved minerals from the ocean rock boundary. When that fluid reaches the cold surface, it freezes quickly and leaves behind salts, tiny grains of silica, and other solids. Over time, radiation and sunlight can act on those deposits, turning methane-bearing residues into complex organics called tholins. That gives a path to the reddish tones seen on parts of Triton. Upwelling material brings carbon-bearing compounds up. Sunlight and energetic particles rework them into darker organics. Wind and frost cycles spread them out across the terrain. If organics are present in the subsurface water, then the ocean would hold not just liquid and heat, but also building blocks ingredients that, on Earth, are part of prebiotic chemistry. This does not claim life. It sets conditions that are friendly to complex chemistry. Long, straight to gently curving lines cut across many regions of Triton. These look like faults breaks where the crust has shifted. Some could form when the shell stretches or compresses due to interior changes. Others could reflect freeze-thaw style processes on an ice world, expansion as water freezes, and contraction as it cools, both of which can stress and crack the crust. Faults provide pathways for gases to move and for cryofluids to find the surface. They also segment the ground into blocks that can tilt and rotate slightly, producing the polygonal patterns seen in a few images. Voyager 2 revealed another kind of activity that may not come from deep plumbing at all. On the lit side of Triton, the spacecraft saw dark, fan-shaped deposits extending downwind for up to 150 kilometers. These fans looked like they were sprayed from narrow vents, leaving long, tapered stains on the pale surface. The spacecraft also caught slender plumes rising as high as 8 kilometers. The leading explanation uses a solid-state greenhouse effect in a very thin, clear ice layer. Imagine that sunlight passes through a mostly transparent cap of nitrogen or water ice and warms a darker bed of material below tholins and other organics that absorb light. The warmth causes the bottom of the ice layer to sublime, turning solid into gas and building pressure in a shallow pocket. When the pressure exceeds the weight of the cap and the strength of overlying ice, the cap breaks. Gas vents upward, entrains fine dark particles, and sprays them into the wind. The result is a jet and a trailing fan. A similar process operates near Mars's poles, where spring sunlight heats dark patches beneath seasonal carbon dioxide ice and drives geyser-like outbursts that paint the snow with radiating streaks. For any jet to rise and carry particles downwind, there must be some air to push against. Triton has an atmosphere, though it is far thinner than Earth's. Surface pressure measured during the Voyager 2 flyby was on the order of 0.014 millibar, about what you would find 80 kilometers above Earth. Even at that low pressure, nitrogen gas can move as wind, shape clouds, and transport haze. Like Pluto's, Triton's atmosphere changes with the seasons. As sunlight shifts over decades-long cycles, nitrogen frost can sublime from the sunlit hemisphere and condense on the darker, colder side. Since 1989, remote observations suggest that Triton's atmosphere grew denser for a time, likely because more of the sunlit frost evaporated and added gas to the air. With a bit more gas, circulation strengthens, and the lower atmosphere can support weather up to several kilometers in height. Voyager 2 imaged bright clouds suspended a few kilometers above the surface, pale streaks and patches that cast faint shadows. It also recorded that many of the dark plume deposits point the same way, evidence for a prevailing wind at the time and place of the flyby. Winds at such low pressures do not feel like breezes to us, but they are enough to bend a narrow jet and lay down a long, thin fan of dust. Over years, those winds help sort particles by size and density, leaving lighter material to drift farther while heavier grains fall close to the source. The air is not completely clear. Triton's atmosphere is hazy. Tiny hydrocarbon particles and other photochemical products float in suspension, giving the air a soft, scattering glow when backlit. These fine particles form when sunlight and energetic particles break apart methane and nitrogen, and then those fragments recombine into longer carbon chains. Early in their life, these products are hydrocarbons, not yet the complex tholins that stain the surface. Given enough time under ultraviolet light, the hydrocarbons can evolve into tholins and settle onto the ground. Meanwhile, fresh haze is made aloft, and the cycle continues. Cryovolcanic activity that lofts organics from below adds to this inventory. Seasonal evaporation and refreezing of nitrogen ice repaints the surface, and winds keep redistributing the finest grains. The result is a small world with a busy surface atmosphere exchange, subtle but constant. Calling Triton a moon understates its character. In size and history, it resembles a dwarf planet that was captured. It likely formed in the Kuiper Belt, alongside Pluto, built from the same blend of rock and ices. It carries a rocky, probably metallic interior under a thick water ice shell, wrapped in a skin of volatile nitrogen and methane ices that move with the seasons. It shows active or recent cryovolcanism, whether from deep sources that feed young plains and calderas, or from shallow greenhouse-driven jets that streak the ground. It has an atmosphere that supports clouds and winds, a haze made by sunlight, and surface colors that record ongoing organic chemistry. Its orbit is retrograde and highly tilted, a dynamical signature of capture. All of these factors, taken together, make Triton one of the most unusual worlds in the solar system, less like a typical satellite and more like a displaced sibling of Pluto, running a full suite of cold processes far from the Sunday.